All right, everyone, it is my pleasure to announce our next speaker, Rose Kaplan-Kelly, who will be telling us about right-angled links in thickened surfaces. Thanks, Rose.
Thanks, and thank you for this opportunity to speak. I'm going to begin with a little bit of motivation behind this work. So that starts with this question, this context of how much we can learn about a link complement from the link diagram. And as we saw yesterday, a family of links that have lent themselves especially well to this are alternating links. So this makes sense in this context to see if we can find broader families of links that still have these alternating properties and find ways of connecting the information we get from the diagram of a link to the geometry of its complement. Another motivation is finding totally geodesic surfaces in link complements. So we'll talk about that. And also addressing this question, which was posed by Champanerkar, Kofman, and Purcell, who asked if there were links besides two specific links that have a certain right-angled structure when you see them as alternating on a torus in a thickened torus. So we'll be addressing that question. Throughout this talk, we're going to talk about links which are alternating on a surface F with genus greater than or equal to 1. So we can see pictures of these generalized diagrams here. This is a genus 3 projection surface, a genus 2 projection surface with our links in green on them. And we'll think of our links as being in the thickened surface on the projection surface at F cross 0. We say that such a diagram is alternating if for every boundary component of every region, we can give an orientation such that crossings alternate between under and over. So on the left, we have a non-example. If I take this region, I give it this orientation, and we follow my mouse around, we can see that I have undercrossing followed by undercrossing, so it fails the condition. Whereas on the right, if we choose any of these regions and we travel around, we see that our crossings alternate between under and over. We're going to be interested in the class of links which are cellular weakly generalized alternating, which was introduced by Howie and then also by Howie and Purcell more generally. So we'll be using their definitions, but for this case of links in thickened surfaces. We say that a link is cellular if all of the regions in its diagram are disks. So on the left here, or on the right here, I should say, we see that this fails that condition because this region right here isn't a disk, it's an annulus. We also want our links to be reduced, which means that this link fails as well because it has a component which has no crossings. We want all of our components to have crossings. So we can't have something like this component right here. We also want our links to be weakly prime, which means that for any disk in our projection surface F, such that the boundary of the disk intersects the link twice transversely. So for instance, here we can see the boundary of our disk in blue intersecting this green link transversely twice. We want the intersection of the link with that disk to be an embedded arc. So you see that that condition is failed here, so this link is not weakly prime. And for the rest of this talk, we're going to assume that our links are cellular, weakly generalized alternating, so they satisfy these properties. Part of why we want the links to have these properties is that these will be links that are checkerboard colorable. What that means is that I can color in the regions of the diagram, either white or shaded, such that with respect to a crossing on the diagonal, our links have the same color, versus when they share an edge, they don't. From the checkerboard coloring, we can then form two checkerboard surfaces by inserting twisted bands that connect all of the faces that have the same color. So I get a shaded checkerboard surface and I get a white checkerboard surface by inserting these twisted bands. Notice that these two checkerboard surfaces will intersect precisely at each crossing in an arc that runs from the understrand to the overstrand of the link. So here in this picture, you can see that this shaded surface and this white surface that we build in the link complement will intersect at these arcs running from under to over for the link strands. In order to find decompositions of the complements of these links, we need this notion of a generalized polyhedron. So you might have seen decompositions before into polyhedra. Now we need to generalize that notion. And a generalized polyhedron will be homeomorphic to a cone on the torus, with the cellular graph on this F cross 0. So here in this picture, we have a cellular graph here, and you see the cone on this surface. We'll say that it's ideal if all of the vertices of that cellular graph have been removed, as well as the apex, as well as this blue vertex at the top. If that vertex is ultra ideal, then we'll have a semi-truncated polyhedron when we truncate that ultra-ideal vertex. So I'll have truncation here. Howie and Purcell generalized a polyhedral decomposition to a broader setting. And for our links and thickened surfaces, what this means is that we can decompose our complement into two generalized polyhedra, which I'm calling P plus and P minus, with cellular graphs on their boundaries corresponding to F cross 0, where those cellular graphs correspond to the diagram of the link. So in our picture here, where I'm just showing part of those cellular graphs, those correspond to the link diagram that we had on this surface F. And to recover the full complement of the link in the thickened surface, we glue P plus to P minus via homeomorphism, which is a composition of the identity with a rotation on these faces. So you can see that rotation occurring via the coloring I've put on this face, where we turn and then glue. The cellular graph corresponds to the link diagram, so we also get a coloring on this graph on the regions, either white or shaded, that corresponds to that checkerboard coloring that we have for the link diagrams. So if I drew out more, you would see that some of these faces are white and some are shaded, corresponding to the checkerboard surfaces. Another decomposition for these links is through face-centered bipyramids. And this is due to Adams, Calder, and Meyer, and then also to Champanerkar, Kofman, and Purcell for the torus. What we do here is in our link diagram, so here we're seeing our link in yellow, we cone each face above and below to form a bipyramid on that face. Then we glue together the neighboring bipyramids to recover the full complement. If our projection surface is the torus, then the apexes shown in blue here are ideal. If our projection surface has higher genus, then we get ultra-ideal vertices. So this is where we're going to want to truncate. So we get a truncated face above and below. And when we glue all of these bipyramids together, those new boundary faces will glue to form our F cross 1 and F cross negative 1, those two boundary surfaces for the complement of this link in a thickened surface. So far I've talked about topological decompositions of the complement of these links, but we're interested in the geometric structures we can get on the complement. So Adams et al. And Howie-Purcell showed that these links are hyperbolic. So these links in the thickened surface have a complement which admits a complete hyperbolic structure. And moreover, when the diagram has regular faces, they showed that this bipyramid decomposition that we just saw can in fact be realized as a geometric decomposition. So we can get the complete hyperbolic structure on the complement by gluing together those bipyramids. So now we have this idea of a hyperbolic generalized polyhedra where each of them have this convex hyperbolic structure, and will require that our boundary be totally geodesic. The reason for that is that we want to have a unique complete hyperbolic structure. So we have that requirement. In order to look at this, we'll need this notion of a gear shift map. So what we do is we have our two generalized polyhedra, P plus and P minus, and we suppose that we could glue them where corresponding faces glue, where if they had K sides, let's say, we glue them by a 1/K rotation on each face, either clockwise or counterclockwise, depending on which checkerboard surface they correspond to. This gluing is called gluing by a gear shift rotation, or I might call this the gear shift map. A link is called completely realizable if the complete hyperbolic structure on its complement is given by gluing hyperbolic generalized polyhedra by that gear shift map, and those hyperbolic generalized polyhedra have the combinatorics of the generalized checkerboard polyhedra that we saw before. So you decompose the complement along these checkerboard surfaces. So we found P plus and P minus. With the same combinatorics, we actually have that they're hyperbolic. We glue them via this twisting, and we get the complete hyperbolic structure on the complement. If, in addition, these links have all right angles, as the two P plus and P minus, the two generalized polyhedra have all right angles as their dihedral angles, then we say that our link is right-angled, generalized, completely realizable, which I shorten to RGCR. A natural follow-up question is, which links are RGCR? In the setting of links which are alternating on S2 and S3, Gahn showed that these are precisely the three links with this property. So these are the three links that are right-angled, completely realizable. So taking a step back, this shows that this is a very special property. Not many links have this. So among alternating links, this is it. Champanerkar, Kofman, and Purcell considered links that are in the thickened torus. They considered biperiodic alternating links and semi-regular links. So links that are invariant under a two-dimensional lattice. So you take a tiling of the Euclidean plane, it's invariant under this lattice, so you get a corresponding quotient in the torus. And then here we see an example of a semi-regular link where you have that all of the faces are regular. So imagine we start with a regular tiling of the plane by regular hexagons and triangles. In place of every vertex of that tiling, we now put in crossings, and we put them in such that it's alternating between under and over. And then to find corresponding links in the thickened torus, we take quotients. So here you can see a fundamental domain and then a corresponding link in the thickened torus. What they showed was that among semi-regular links, the two links that are RGCR are the square weave and the triaxial link. The square weave is the link corresponding to this tiling by squares, and the triaxial link is the link corresponding to tilings by regular hexagons and triangles. So they showed that these are the two links that have this decomposition. They're RGCR, but they say torahedra, which is generalized polyhedra for the thickened torus setting. And they also showed that these links have two totally geodesic checkerboard surfaces. But they ask, are there links that aren't semi-regular, right, among the larger class of biperiodic links that also have this property? We might also ask, what about if our surface has higher genus for our projection surface? So here, instead of starting with the tiling of the Euclidean plane, we start with the tiling of H2. And we'll have this example here. Imagine that our tiling was by regular octagons. Now we take a fundamental domain of just 4 of those octagons, and I've shown how we could glue the different edges to get a corresponding link diagram on this genus-free surface. So we could glue these two edges and these two edges, and then I've colored the different edges to show how they glue up to get that final diagram on that surface. This leads us to our theorem. So we start with our link L, which is a cellular weakly generalized alternating link in this thickened surface F cross I. And then the following are equivalent. First, that the link is RGCR. Second, that the link has two totally geodesic checkerboard surfaces. And then third and fourth, we have these diagrammatic restrictions. So once again, stepping back, what this theorem is telling us is we have this equivalence between having a nice right-angled structure on the complement of the link, being RGCR, having two totally geodesic surfaces in this link complement, and having diagrammatic restrictions. It's tying those three things together. What these diagram restrictions are the third one is, first, we have that our checkerboard surfaces contain precisely one type of polygon. By type, I mean number of sides. So our white checkerboard surface might have all n-gons, our shaded checkerboard surface might have all m-gons, and we might have that n is equal to m. That is allowed. This fourth condition says that in our diagram, we have at most two types of polygons. At every vertex, we have the same configuration of polygons. This is this n-m, n-m pattern. And all of these faces are regular. Now, I won't have time to go through the entirety of this proof, but I thought that I would give some of the ideas behind it. So first, we're assuming that our link is RGCR, and we want to see why that implies that it has totally geodesic checkerboard surfaces. So we know that our link decomposes into two right-angled hyperbolic generalized polyhedra, and that there's a coloring on that boundary component corresponding to the projection surface F that's white and shaded. So take those two generalized polyhedra, and let's say we just glue them along their shaded faces. Well, by assumption, all of the dihedral angles are right angles, so that means that all of the white faces will glue together at a pi angle. So as we build that white checkerboard surface, we're going to get that it's totally geodesic because we have this nice flat gluing for all of those faces. And the same would be true if instead I had said, let's start just by gluing the white faces and build the shaded checkerboard surface instead. Next, we're assuming that we have two totally geodesic checkerboard surfaces, and we want to see why that implies anything about the diagram of the link. So tools that go into this are, first, we want to show that if our link has two totally geodesic checkerboard surfaces, then the faces of its corresponding generalized polyhedra in this decomposition of its complement are regular. And then also, we want to extend Don's work to show that if we have that our link has two totally geodesic checkerboard surfaces, then two faces that are diagonal in the diagram with respect to any crossing corresponding to a vertex will have the same number of sides. So for that first result, what goes into that is using that if we have two totally geodesic checkerboard surfaces, then we can show, in fact, that our link is completely realizable, and that the two hyperbolic generalized polyhedra that we get are isometric. So going back to this picture, we show that if we have two totally geodesic checkerboard surfaces, then in this decomposition into P plus and P minus, we not only have that they glue by the gear shift map and have the combinatorics from the checkerboard surfaces, and then give us the complete hyperbolic structure that's completely realizable, we also show that P plus is isometric to P minus. And we can use Gon's insight that from the fact that P plus is isometric to P minus, and that they glue with no shearing, every face glues via rotation with no shearing, we can in fact build an isometry on every face that's a rotation, which implies that every face must be regular. And finally, we want to start with the idea that we have a set of restrictions on the diagram of the link and see why that implies anything about the hyperbolic structure on the complement of the link. So we start by assuming that we have a set of regular faces in our diagram and that they're all arranged in this pattern of an n-gon next to an m-gon, and then an n-gon and an m-gon again. Well, we have a regular diagram, so we can use that bipyramid decomposition to get the complete hyperbolic structure on the complement of this link. So on all of these regular faces, we build a bipyramid. Now, from the work of Adams, Cauldron, and Mayer, we know the dihedral angles on those bipyramids. So here we're seeing they're built on neighboring faces and how they would be glued. And then here I've labeled the different edges, and we see the different dihedral angles that you get on those edges, which are all in terms of the face that the bipyramid was built upon. To find the two checkerboard polyhedra, what we want to do is we want to slice along the checkerboard surfaces. So we're slicing along the face that has these pink vertices, precisely taking these bipyramids and cutting them into two pyramids. So we get a collection of pyramids, which we can think of as like above, and a set of pyramids that we can think of as like below. And gluing together those pyramids will give us P plus and P minus, those two hyperbolic generalized polyhedra that we want for the decomposition. While doing so, we're slicing along this edge D, so we're taking half of its dihedral angle. And that dihedral angle is in terms of the interior angle of the face that it was built on. So we know that all of these pyramids are going to have this dihedral angle pi minus alpha n over 2, and pi minus alpha m over 2, where alpha n is the interior angle of this regular n-gon, alpha m is the interior angle of this regular m-gon. And we also know that this tiling has to have that n-m-n-m pattern, so we know that 2 alpha n plus 2 alpha m gives us 2 pi. So in our calculation for the dihedral angles we get when we glue together the pyramids, we find that all of them are pi over 2. So this tells us that our link is RGCR. An application of this work is that now we can answer that question. So we find that L is RGCR for a projection surface, the torus, if and only if it's the triaxial link or the square weave, because we showed that it must have regular faces, and Champanerkar, Kofman, and Purcell showed that among the semi-regular links, the links in this thickened torus that have those regular faces, these were the only two that had that property of having this right-angled structure. And I'll end here. This is a table of different tilings that correspond to projection surface of genus 2 or genus 3. Thank you.
Let's thank our speaker. Wonderful. Any questions for our speaker? If not, let's thank our speaker again. Thank you, Rose.